First, I want to thank the organizer for giving me the opportunity to speak here. What I'll be talking about today is work that was done together with Benjamin Basu, who is here, Simon Karen-Hott, Lance Dixon, and Pedro Vieira. It's actually work that started 2 years ago or more, and hopefully we will be soon write it up. So the basic thing that we are studying is the factorization limit in gauge theory. In that, here we will focus, of course, on n equal to 4 superior meals. And when I mean factorization, factorization is a limit of some observables, and we have we'll consider several examples where some distance or some momentum goes to 0. So momentum square goes to 0. And in this limit, one of the main punchline would be that there are some few universal building blocks that control these limits for any observable, and therefore allow us to give predictions at finite coupling. And integrability in particular will allow us to fix some of these building blocks, and therefore have more or less full control on this limit for any observable in the theory. So in this talk, I'll give one example that we will follow in details, and then several other examples which will be more like, given the time, comics, just the general structure. So let's start with it's not working. A few examples. So one of the maybe most famous examples, okay, this will not work, is the factorization limit of scattering amplitudes. With some subset of momentum, the sum of them go on shell. One of the very famous properties of perturbation theory is the amplitude factorized on a pole into 2 sub-amplitudes. So this here are some subset of momentum that go on shell and goes to 0 in the massless theory. Another example, this will work, is basically the T-dual of the picture above. We were talking about planar n equal to 4, which you have a polygon, null polygon Wilson loops, and 2 fixed casts become null separated from each other. And in this limit, one would expect the Wilson loop, in analog to the picture above, to, if you're studying here with the hexagon, to factorize into 2 squares. So these 2 pictures above, going too fast, are T-dual to each other in planar n equal to 4. Another similar limit that were considered, I think, by several people here, studied with the work of Aldai and company, consider the null limit of correlation function of local operators. So here we have, for example, the 4-point function of 4 local operators, and one can take the limit where pairwise they become null separated from each other. And one of the hallmark of those works was that in this limit, you get a pole for each pair of 2 operators that become null separated from each other, and the residue of the pole is a square Wilson line. Consider another example, which is called sometimes the hard scattering singularity of correlation function. And I think it was studied by Joa and Polchinski, then by Joa and Costa in the papers on the Econal limit, where again you consider 4-point function of local operators. Now you take the limit, which we call z goes to z bar, where there is some point in the back that becomes null separated from the 4 points. And at that point, you have a singularity that you would like to control. Maybe one other similar limit is the mixed correlator of a square polygon Wilson loop and a local operator. This was again studied by Fernando and Arkady here. And you can take a similar limit where the operator becomes null separated, for example, from 2 cusps of the square. The question, what happened in that limit? We have 2 more limits. One other interesting limit is when you have here a hexagon Wilson line, you can take the limit where 2 of its edges self-cross each other. In that limit, you would expect it to factorize into 2 squares. Okay? And the T-dual of the same picture is called the double parton scattering. So you start with a 6-point amplitude, and then you take a limit where one of the momenta can split into two collinear momenta, and then you have factorized two 4-point amplitude that physically are separated by a long, large transverse direction. So these two pictures again are T-dual to each other. And what you will see that all these cases are decomposed from some simple universal building blocks. And what's special about planar n equal to 4 superior means that I'll focus on, as opposed to other theories, is that we can compute them explicitly. Determine all the constant and give all loop predictions, finite coupling predictions for all of these limits. So during the main part of the talk, I'll focus on one example, which is the factorization limit of scattering amplitude. So here, for example, we have 6-point amplitudes. First, for 4-point or 5-point amplitudes, you cannot have such a factorization limit because of supersymmetry. And there's no way to, and also kinematics, there's no way to factorize it on two amplitudes. The first time you have such a factorization is the 6-point. If you look also on the helicity, you see that the first time the residue would be non-zero is at the next to MHV level. So you have some set of P1, P2, and P3 go on shell, factorized into product of two 4-point amplitude. Okay? So this is certainly what happened at 3 level. What happened when you start to include loop corrections? So first, this factorization is one of the hallmark, the bones of perturbation theories. This is what BCFW is based on. And there are some that call it hallmark of locality of the theory. What happened to this pole when we start to include loop corrections? What happened is that the residue of this pole, apart from the pole and the two 4-point amplitude, is dressed by some function of the Mandelstam invariance of the momentums. Okay? So this will be tough. So this is something we would like to determine. And before doing so, of course, such an amplitude, when you go to loop level, have higher divergence. So let me first discuss how we regularize such an amplitude. And the way I want to regularize it is in a way, not in the standard way, in a way that will allow you to isolate the physics of this factorization limit. So we define a ratio-like function. The usual ratio function is defined by the NMHV divided by the MHV amplitude. Here, instead of dividing by the MHV amplitude, what we divide is by what is called the BDS-like amplitude. The BDS-like amplitude is a solution to the anomalous dual conformal anomaly equation, and therefore when you divide it, you remove all the divergences. But what is special about this function is that it's only function of such products of S, I plus 1. So it doesn't know about S1, 2, 3. It doesn't know about this P square that go there, and therefore this is a nice regularization that will not contaminate the factorization limit. This is why it's nice to use it. Of course, you can use any other and then translate. So what happens when you divide by the BDS-like? The result, of course, starts with 3 level, where the 3 level NMHV has this factorization pole, already 3 level, and then it's dressed by some function of the conformal cross ratios made of the external momenta. And what are the conformal cross ratios? So let me try to do it here. Again? It doesn't really work. I see, okay. Good. So here is the hexagon, parameterize the 6 momenta in the scattering amplitude. So we can consider, for example, U2, which will be these two distances, this one and this one, divided by the two dashed line here. This is one cross ratio that you can form, and there are two other independents which are just rotating this picture to the right and left. So for 6-point amplitude, or for the hexagon-Wilson loop, we have 3 independent cross ratio, which we call U1 and U2 and U3. And now the regulated amplitude, apart from the 3-level part, is a function of these conformal cross ratios. Now, how the factorization limit look in terms of this conformal invariant data? So here we have to talk about the conformal generalization of a distance. We have the point here on the bottom and the point on the top of the hexagon that become null separated from each other. But in order, what this y conformal cross ratio does is promote this distance that goes to 0 in the factorization limit into a conformal cross ratio, but it does so only using next to nearest distances. So we have this, if I could, so we have this distance. Imagine that look on any corner in this polygon, there is one solid line and one dashed line that go out of it. So it appears once in the numerator and one in the denominator. And therefore, when you take the ratio of all the solid line by the dashed line, you get a conformal cross ratio. And you see that only the distance between the bottom and the top is a factorization distance that appears in this conformal cross ratio. So this is a good conformal invariant variable to control what happened in the factorization limit, and it goes to 0. In the previous notation, this is just U2 over U1, U3. Now, this factorization limit was studied like 2.5 years ago by Dixon, Van Hypel, and McClone. And what they found in perturbation theory is that this function U that appeared there is, at any loop order, is just a polynomial of log of this cross ratio that goes to 0 in the factorization limit. And since they were, then they had another paper, right now they were working up to 4 loops, and this is the result for these polynomials up to 4 loops. This variable x is log of the conformal cross ratio, one of the conformal cross ratio that goes to 0 in the factorization limit. So if we have a prediction, we better reproduce this perturbative data. Okay? So the first question I want to ask is how this limit now looks at finite coupling. So instead of going through the derivation, let me first just present the result and understand what it tried to tell us and what is the physics, and then go through the derivation. Okay? So the result that we suggest is the following. This function u, or here in purpose dressed by the pole. The pole is just 1 over square root of y. Y is like the distance square that goes to 0 in the factorization limit. So 3 level, at leading order, we just have the pole. And the claim is that the factorization limit, as y goes to 0, at any value, any finite value of the coupling, this is controlled by this very simple integral. Integral du e to the minus u times square root of y, and then there is some coefficient that multiply log square of u, and a coefficient that multiply log of u. That's it. This quantity I'll call I of g and y. And it's not so important to the talk, but this constant will be determined from integrability, and they are given by explicit functions of the coupling that are very familiar to any of you who study the GKP string. So what is the properties of this integral? Let's see what it tried to tell us. So first note that in perturbation theory, all these coefficients there, all the gammas, start at order g squared. So at leading order, if we put all of them to 0, we could just rescale u by square root of lambda, by square root of y, excuse me, and reproduce the pole. You see at leading order, you reproduce the pole, and now we start to expand. In perturbation theory, we'll bring down from the exponent power of the coupling times log of u squared and single log of u. And after you rescale u by square root of y, you would reduce polynomial in log of y. Okay? And this automatically reproduce all the result of Lance and his collaborators and give you immediately in one shift enter all loop prediction for the residues of this factorization point. Okay? So this seems great, but note something interesting. At any finite coupling, perturbative was taking first g to 0 and then looking on the factorization point. But if I'm doing the other thing, I'm letting g to be as small as you want, but keep it finite, and go to the factorization point, the integral before was divergent because of the large u region. Now we have this minus gamma cusp times log u squared. This term is enough to make the integral finite. In other words, at any finite value of the coupling, there is no pole. The pole is completely gone if you are not working in perturbation theory. Mm-hmm. Note that this integral was like picked as the leading contribution in this limit, but there is other background that is like not factorized, that is of order 1 in this background. And since this integral is finite, at generic g, and in particular at large g, it's not even the leading contribution to the amplitude in this limit. In other words, if you would have resummed perturbation theory, you would not get even the leading contribution for generic g for the amplitude in this factorization limit. So first question that comes to mind, is there something really happening there at finite coupling? And indeed, something happened there, and what happened there is that the finite coupling result has a discontinuity around this point. What we can do, we can take this I, this integral, and compute a discontinuity in y around this point. When you compute the discontinuity, you find that this integral indeed has a discontinuity, and this discontinuity is exponentially suppressed by gamma cusp times log of the distance to the factorization square. In other words, there is a discontinuity, and it's exponentially suppressed as you go to the factorization limit. If you think a bit, this is also what you would expect from physical arguments. So if you compute the discontinuity of this integral, we see a bump that at 0, as p squared goes to 0, is strictly 0. But as we take g to be smaller and smaller, it has a bump that becomes larger and larger, and if you first expand in g, you will see a delta function for the discontinuity coming from the pole. Basically, we are creating here an on-shell particle, but if you are studying it not in perturbation theory, it rests by all the soft and collinear physics that suppress this on-shell propagation. And this is what we are seeing. The interesting thing is that there remains a discontinuity around this point. So I think the physical way to talk about factorization at finite coupling is to talk about the discontinuity. If you talk about what happened to the amplitude itself at this point, or to any other observable, nothing special happened there. This special discontinuity by itself is a negligible contribution when you go there. Okay? But it has a discontinuity there. So what is the meaning of this integral? Where it came from? What we will see is that this parameter u, we first derive it from integrability, where it will be related to the spectral parameter in integrability, or the momentum of flux subexcitation. On the other hand, we see that you can also identify it with some just propagation time or energy, depends on which T-dual picture you are looking at. So what I want to do now is derive this integral starting from integrability, namely from the operator product expansion of scattering amplitude or polygon Wilson loops. So just a flash, I'm sure that all of you heard about it many times, so I'll just flash the main idea. When we talk about the OP, we consider such a polygon Wilson loop, and we think about two of its edges as creating a flux. And then the rest of the polygon creates some excitation that propagates from the bottom to the top. More explicitly in equation, if we have here an hexagon, we divide it into two pentagons as drawn here, and we parameterize the free conformal cross ratio u1, u2, and u3 by a free parameter that we call the flux time tau, the flux space direction sigma, and some angle that is called phi. In that limit, what we do, we expand it at large tau and write it as a sum over all the flux subexcitations, which can be scalar, fermion, or gauge field, some amplitudes to emit them and absorb them at the bottom or the top, and their propagation by an energy E conjugate to tau, momentum P conjugate to sigma, and some angular momentum conjugate to phi. Now, before talking about what happened in this limit, we have to talk about regularization. When we usually regularize the result in the OPE, we take some ratio between the hexagon and the two pentagons and multiply by the square. This is slightly different from dividing by the BDS-like, but apparently the difference between the two is very, very simple. U would have been what the result would have been if you divide by BDS-like. You see the difference is just 2 gamma cusp times tau squared plus sigma squared. Mm-hmm. So we know how to translate between the two regularizations. Now, what happened if we first now go to the collinear limit, we first take tau to be very, very large, this is the limit where we flatten the bottom and the top of the pentagon. Now the factorization limit is the limit where this point on the bottom and point on the top become null separated. And this is controlled by sigma. Sigma is the relative direction of this point on the bottom and on the top. To be more explicit, if we look on the square root of y, which is the parameter that goes to 0 in the factorization point, at large tau is just given by e to the minus tau times cos sigma. So you see that the point on the bottom and the collinear limit and the factorization limit are kind of orthogonal direction to each other. This is what allows us to approach the factorization limit from the collinear limit. Because the two limit compute, we see there are two different directions. And from this, we see that what we really need to take, if we first took the collinear limit, which means large tau, we need to take sigma to minus I pi over 2. Minus I pi over 2, the cosh will go to 0, and therefore the point on the bottom and point on the top will become null separated. So we have to study the previous OP expansion in that limit. So let's see what happened by starting by looking at a 3-level example. Okay? 3-level example, if we study this NMHV amplitude, we just have a free propagation of a scalar from the bottom dot to the top dot. And once you parameterize this free propagator using tau, sigma, and phi, and take tau to be very, very large, you find e to the minus tau, minus 1 times tau, 1 is the energy, flux tube energy of the scalar, divided by cosh of sigma. And the rules in the OP is to write it in momentum space. So when you do a Fourier transform, 1 over cosh of sigma mapped to 1 over pi, again, cosh of pi p over 2. And what we see here that the fact that we have on the left-hand side a pole where sigma goes to minus I pi over 2 is reflected in momentum space by the fact that when you take p and you take sigma to minus I pi over 2, the integral barely converges at large p. In other words, this pole is dominated by very, very large momentum. This is also intuitive because we want to localize the bottom excitation in front of the top excitation. To localize it, we have to give it a very, very large momentum. This is very, very large flux tube momentum. And this is very nice because all the complicated expressions that describe the probability to create the excitation and its dispersion relation simplify drastically in this limit. Basically, what one gets is that in this limit, the momentum is just 2u, and the energy is just gamma cos log u plus a constant. And once you plug this back into the formula, you immediately land on this integral that I wrote before, which was the I of g and y. You see that the u integral is basically the spectral parameter, or up to factor of 2, is the momentum of a single flux tube excitation that propagates from the bottom to the top. Okay. So this was all for MHV, next to MHV so far, but you can do the same game for MHV. For MHV, there will not be a pole at 3 level, but at finite coupling up to some simple factor, the result look almost the same. So at finite coupling, MHV and next to MHV both have a discontinuity around this point and behave almost identically. So next I want to ask, what is the physics behind this I, if you didn't know about integrability, and could we predict it a priori, the structure, without having the OP? So the main player in the game is what we will call a jet. What happened in the factorization limit, that let's say S1 to 3 goes to 0, is that we have an excitation that propagates for a very, very long time. But this excitation is not just a single gluon. This gluon have one thing is that it get dressed by all the collinear and the soft physics. It can split into many, many collinear, and it can emit many soft gluons. So this whole thing that propagate, we will call a jet. It's the initial gluon, or in that case, a scalar, and all the radiation that surround it. This is just wording, but to be more explicit, we defined what is called we call a jet creation of an operator. This is J, and the index n is some null direction, which is just integrate the scalar field around some null direction with a phase that corresponds to the energy of the jet. And to make it gauge invariant, we attach to it a Wilson line, null Wilson line that go all the way to infinity. So in that case, it's a scalar, but this you can do to any other field, the gauge field or the fermion. And this operator is not as strange. This is one way to think even about LSD reduction formula. If you take this operator and place it at null infinity, you can show that the creation operator of an asymptotic state is exactly given by this operator integrated at null infinity. This is something special about massless particles, that they all come from a single direction, and therefore instead of integrating over all space and then taking the momentum on shell, you can just integrate the field in that direction at infinity, and it will create a good asymptotic state. So this formula for the creation operator here is equivalent to the LSD reduction formula. It's easy to prove. And so the jet function is just this, if you want, creation operator being conformal transformed to some finite point in space-time. What we need now for the factorization is this jet to propagate some given distance or given energy. So what we will do is to compute the two-point function of such a jet. Now the two-point function of such a jet have both the collinear and the soft divergence. It have a UV and IR divergence. We want now, for now, just to capture the UV, the collinear divergence. So we take the two-point function and we divide it by its equinal limit. So here we have two jets separated by some distance in a null direction. And we divide it by the equinal limit of this picture, which is just a U-shaped Wilson line of two parallel Wilson lines going to infinity along this null direction. This ratio removes all the IR divergences. So this function now can be, you can write an RG equation. It still depends on the UV cutoff, and integrate it, and it takes the following form. Here E is the energy in one null direction, and L is the separation in another. Importantly, mu is the regularization scale, the UV regularization scale. So this captures the collinear hard physics of the jet. Another thing we want to do is to capture the IR physics, the soft physics. This is, of course, captured by, again, a U-shaped Wilson line, but now the two edges of it are not parallel, but they are in the direction of the two neighboring momenta of the particle that is going on shell. So this, I call it S here. It's just a U-shaped Wilson line where this is two semi-infinite Wilson lines going in direction P3 and P4, and the atom here is separated by some distance L in another null direction. Again, one can write a simple RG equation and solve for this quantity, and given again in terms of the momentum invariance S34 in that case, and the regularization scale that we call mu here. Again, of course, controlled by gamma cusp and the GKP properties. So basically, that's it. Now we can glue these building blocks together and see what happened in the factorization limit. So we started here with a 6-point amplitude, and the claim is that in this limit it's factorized into two 4-point amplitude times one jet that propagate and capture all the hard collinear physics times two U-shaped Wilson lines that capture the soft IR divergences coming from the two sides of the on-shell particle. In equations, we claim that M here is the renormalized amplitude that depends on the cutoff. Claim that in this limit, the amplitude factorized into two 4-point amplitude. This is M4 on the right and M4 on the left. Here we have the jet times the two U-shaped Wilson lines. And since what is determined in this limit is the energy of the jet and not the distance it propagates, we have to Fourier transform from the distance L to its energy, which is given by the momentum transfer here. And when you plug these building blocks inside, you follow up exactly on the same integral that we got before from integrability. The only thing that this general RG equation did not tell you are what are the constants. There are some skin-independent constant that is unfixed by this RG argument. So this is, this is what I wrote here at the end as C double prime. And once we compare the two, the C double prime is one of the quantity that was computed from the GKP, which is called gamma 3 before. We can also study the same picture in the T-dual. In the T-dual picture, again, the claim here is that the hexagon factorized into two squares. We have in the middle a jet. And now the new ingredients is what is called the soft current. The probability of two null lines or two hard partons to create such a jet. One way to define it is just to take the ratio of the 4 and the 5-point amplitude when the extra momentum of the 5-point amplitude on top of the 4 is taken to 0, or all other momentum taken to infinity, and they can be replaced by a null Wilson line. So this is called the soft current. And again, one can solve for it. It's given by some constant gamma cusp, G econal, and some other constants that I will not go into. And you put the pictures together. Now you propagate some given distance and not some given energy, so you have to integrate over the energy to this distance, and you reproduce this integral u that I wrote before. Okay? Actually, these two pictures are just T-dual to each other. Of course, the two squares are T-dual to two 4-point amplitude. This jet turned out to be T-dual to itself, where the soft current are just the T-dual of the U-shaped Wilson lines. So we see how in this limit the factorization is really built by putting a few universal building blocks together, doing some integration, and getting the final coupling answer. And what integrability tells us is really how to fix the constants that are coupling dependent in these building blocks. Wow. So given the time now, I'll flash through all the other observables, but it will be only at the level of this picture. We'll not go into much detail or how they are derived. So the other limit we consider is the null limit of the 4-point function, and the claim that in this limit it factorizes into two squares, because it's something in the adjoint, times 4 jets, and times 4 form factors, which are the probability of the operator to create two partons, two jets like that. And again, it can be it's defined by this probability. You can integrate, write an RG equation for it and integrate. And when you put all the pieces together, you reproduce the all-loop final coupling result that were previously put forward by Alde and BC. And then what the Alde and BC result give you again up is a way to fix the constant. So we know the probability for a local operator to create these two, also the constant part in it, which is scheme independent. Now this hard scattering limit, what we expect to get is now 4 squares, 4 form factors for each of the local operators. We have each one of them split into 2 jets, so they have 8 jets and 2 for particle amplitudes. And of course, when you put them together, you go and compare to the perturbative data, and it all match. The null limit of a square and a local operator is expected to be 2 squares, one here on the right, one here on the left, 2 jets, 1 form factor, and 2 soft currents. All of these are building blocks that already was fixed before. Up to the constant, we just put them together, do some integration, and it already produces the known data. Last thing is this double parton scattering. This really, as opposed to the previous example, involve a new ingredient. So what happened here, you have a particle that is being split into 2 collinear parts that are separated by a large separation in the transverse direction. Then you have these 2 4-point amplitude taking place at a very large distance from each other, and the result factorized on them. What you expect is, again, to have these 2 4-point amplitude, to have a square for the square in the middle, to have, we replace the 2 external jets now by 4, so we have 4 jet over 2 jet, and the new ingredient is this probability for the parton to, I wrote it, no, I didn't write it, I'll write it in a second, to split in that way. And the T-dual picture of the same thing is the self-crossing. We expect it to be 2 squares, time a 4-point amplitude, time again 4 jets over 2 jets, time the probability of the Wilson line to break in that specific way, which is just the T-dual of the splitting. And this splitting, again, is the distribution amplitude for a parton to be split into two parts, let's say ZP and 1 minus ZP, that are separated in the transverse direction by some distance that are called X-perp. So this is something that I didn't try hard, but don't know how to determine a priori. What allows us to solve for this case is, again, integrability. It turned out that this self-Gaussian limit is, you have a corner when it's overlap with the multi-regi limit or the BFKL limit. So the self-Gaussian limit is a limit where you take some parameter, I'll call it delta to 0. In terms of U1, U2, U3, you take U1 to 1 and U2 to be equal to U3. The multi-regi limit is very similar. You take U1 to 1 and U2 and U3, not necessarily equal, but both goes to 0 in some specific rate. So we see that the two overlap. If in the Regi limit we ask for U2 to be equal to U3, we tell you that this omega is just a phase. So, of course, we know from integrability, it's what I talked about 2 years ago, the Holop prediction for the amplitude in this BFKL or multi-Regi limit. So we now can go and take this limit where delta goes to 0 and omega is just a phase. So this is the result that we got then. And if you translate to the conformal cross ratios that are written here, which are sigma and var phi, this is the limit where both of them goes to 0. And the limit both of them go to 0, here we have both an integral of some spectral parameter and a summation of many, many modes with different angular momentum. It's controlled by large U and large N. In this limit, you can replace this summation by an integral where R equal to the I phi. I'll call U plus IN over 2. And you remain with the following simple function. J is a Bessel function. And this effective phi is again given by a very similar expression. Again, this was studied by, recently by Dixon and Ashton. And this integral exactly match all the result and give you all other loop result. We can now go back and find what is this splitting distribution function to read it by answer analysis to denote the concept. Okay, so I'll summarize here. We have some simple universal building blocks. That what's nice about n equal to 4 is that we can completely fix them, including the constant. Once we put them together, it seems to have control of the discontinuities of any observable in the planar theory. Thank you. That's a good question. For strong coupling, for example, for talking about the factorization of the scattering amplitude, one has to do something similar to what Shomerus has been doing, to start with the strong coupling TBA and to do analytic continuation and to look on the discontinuity of the result. This is somewhat hard work. One implication of that is that for example, if you take the 4-point function and you go to the null limit, the supergravity at strong coupling will get the result right. It will not capture the discontinuity, but you get the right result. The discontinuity will be captured by a Wilson loop, square Wilson loop, that go between these 4 points. Mm-hmm. I cannot hear you, sorry.
In the track physics picture of factorization, before you determine all the constant using integrability, where does the information of planar equals 4 enter?
It did not.
It did not. So you're predicting the general behavior that...
Yes, similar RG equations and integrate them were, I think were written before in the QCD literature. And so on.
So these are universal, like the general behavior?
Most of them. Something special for n equal to 4, for example, is that the splitting function is determined completely by conformal symmetry, but in other theories, unknown. Yeah, that's, I think, very nice and good question. And it's somewhat related, same question came about when you study the BFKL limit, which we see intersect one of these. As opposed to the OP limit, where we put excitation on the lines, in this limit, when you want to go a bit off the limit, you have to put the excitation or the deformation at the corner or at the point of factorization. We have some ideas, but I cannot say it's understood completely. It's like doing half mirror to put the excitation at the corner. Okay. And that's for the future.
I have an interesting question because there is another famous factorization which was introduced by Leipzig. So when you factorize something with two-prime factors and use some lines with some top. So you know about it, right?
I'm not sure what can you.
So in high-end discussions, there is another very famous factorization for with lines, and they introduced by Leipzig 20 years ago. So when you split your amplitude as two-form factors and use the lines with some tops. Yes, so my question, do you see relations between that type of factorization and
I think this is related to the multi-Reggie limit, no?
it is about Reggie kinematics, yes, you have two high-energy platforms and
yeah. So I think the inclination of this limit only comes about when you go to 6 point, not at 4 point, which is completely in this theory fixed by conformal symmetry. And then this factorization limit and this one have a corner where they overlap. Right? And this is what allows us to fix the last example. Mm-hmm.
Perhaps a minor point, but an MHD amplitude is usually super amplitude. We can yes, super conformal invariant and so on. And same for the Wilson group. So in your approach, you pick some particular component or behaves of Erlang with the OPE or
in this OP derivation, yes, but you don't have to. We want to start it from the pole and then dress it, but you can just consider MHV. At finite coupling, they're all behaving basically the same, up to some small corrections. In particular, at strong coupling, they will all behave the same.
Asking for the questions, so let's thank you.